Hello, I am Manuel Franco Sevilla, a professor here at the University of Maryland, and today we'll be describing the bending of space-time, of the fabric of the universe in which we live, breathe, and love. And so our universe is going to be represented by this rubber surface on which we've drawn these lines so that you can see the curvature on it. This is a surface that right now is just flat because there's no mass bending it. And so you can see that if you place a little mass like this one here on our universe, it doesn't move. Or if it has some initial velocity, it will just follow a straight line like that. Same thing will happen to this bigger but not very large mass. If you place it in the universe, it will stay put. If it has some initial velocity, it will follow a straight line. So next, I'll be placing this very big mass that you see here. This is a heavy one, and I'll be placing it in the center of the universe. It will bend the universe, and then, so before I do that, you need to tell me what you think will be happening to these little masses when, again, I place them in the universe, now bent, without velocity and with initial velocities. Do you think they will stay put, as we saw? They will follow straight lines? Or they will follow different orbits, elliptical, circular, or hyperbolic, and falling across the edge of the universe. So try to think about that for a minute, and when you're ready, I will continue. Okay, great. So let's see what happens when we bend the universe with this big star. So this could be our sun or some other star that we place in the universe, and as you can see, these straight lines are straight no more. And now, when you have little masses, this could be a little planet, which spontaneously appears in the universe without velocity, what would happen to that planet is that it would feel immediately attracted towards the star, and it would go in a straight line towards the star. If this planet instead had some initial velocity, then it would follow some orbit around the star. In this case, you have quite a bit of friction, so it would spiral quite quickly. The precise orbit would depend on several parameters, the velocity in the bending and in the absence of friction in the actual universe. Similar thing happens with this bigger mass. And so you see that now our little masses are following different trajectories. And that's because our universe is now bent. And so the thing that this rubber surface is showing, it's really a key difference that Einstein realized with respect to the theory of gravitation that Newton had proposed. So Newton understood gravitation as a field, just like the electric field. A big mass like this would create a gravitational field. And then if you place another mass, and the mass itself would be like the gravitational charge, then it would generate this action, this force at a distance, and that force would bring that mass closer to the initial mass. Einstein thought that the mechanism by which gravitation works was very different. It looks similar superficially, but instead of creating a field, what it does, it actually bends the fabric of space-time. The space-time in which we live, this three-dimensional space with a fourth dimension of time, gets bent out of shape. And because of that, that's why the planets move in trajectories like ellipses. They think they're following straight lines, but the space itself is curved, and that's why they end up going in these funny orbits. And one proof of that is that in the case of electrical charge, for instance, if you have an electric field and you place a neutral particle, a particle with no electric charge, like a photon or a neutron, it would not feel any force, and the photon would keep going straight. The neutron would go straight in the presence of the proton. In the case of gravitation, this is not true. If you have a massive star like this and you place a photon that has no mass, no gravitational charge, the photon would actually follow this bending of space-time. And because of that, if you have, for instance, a star here that is throwing photons, these photons would follow so-called geodesics that would go around this star in several trajectories, and you could see photons coming from one star as if they appeared coming from many places, and this is called gravitational lensing. Imagine you have the Earth here, and the photons coming from this star here would follow this trajectory here, and in the Earth we would see at least two copies of this star. And you can see here a fundamental distinction between Einstein gravitation, in which the space-time is bent, and the previous conception of gravitation that we had up until Einstein. Okay, I hope you found that interesting, and see you next time.